Thank you. It would actually be awesome if I would have the same introduction every time I'm giving a talk. I have a small confession I like to make. As a professor in theoretical physics, it's actually quite difficult to make people laugh. And so when I saw this picture that was taken at the Minister's Elite Researcher Prize Award in the Royal Danish Opera next to here, I was pretty happy because there are obviously people enjoying what the professor up here behind the green plant is saying. But then, of course, there's this small issue that some of you can perhaps see. It doesn't really seem like the minister is amused, right? Well, so my name is Asger Mortensen, and I have in recent years developed a passion for something quite weird, small metallic nanoparticles. And in particular, I have a curiosity for how light is interacting with these small beasts. And if we can really treat them in a classical way, or we should expect new phenomena that really belongs to the quantum world that we usually in this country associate closely with Niels Bohr and his treatment of atoms. But before diving into that, I would actually be curious to see how many in the audience is actually having a passion for natural sciences. Oh, that's really great. And then I suppose the rest are here for the cocktails and the drinks. Let me show you a small picture that has really kind of motivated me recently in my research, which is something you can see if you travel to, say, in your summer vacation to some of the many beautiful cathedrals we have in Europe. And if you actually take the time to enter and look towards the ceiling, you will see these kind of beautifully colored glass windows, which have been sitting there for years, of course. And usually we are kind of expecting stuff that we color, that this will fade over time. If we leave a piece of plastic in the sun, it will lose its vivid, brilliant colors, right? But these colors are seemingly staying the same year after year. And for me, it's kind of a puzzle what is actually causing these beautiful colors in these ancient glass windows. And this is another example that colored glassware can be quite interesting when you illuminate it with light. So it's a cup called the Lycurgus cup that you can find in British Museum. It's dating back from the 4th century. And the spectacular thing about this is that when you look at it in the first place, it really appears green. And if you then, by accident, somehow put a small light bulb inside so that you illuminate it from inside, it suddenly turns red. And that's kind of weird that you can have a stained material that has this property that in reflection it has one color, and in transmission it has another color. And what is more remarkable is it's not really a new phenomena, right? It has been there for years. Again, it's kind of a puzzle to me how people at that time could actually make these kind of effects. So I got really kind of interested in figuring out what is causing those colors. And this is a slide that is giving some kind of idea what could possibly go on inside those materials. So what I'm showing here to the right is result from light interacting with tiny pieces of gold or silver. So you probably all have a pretty good idea what gold and silver looks like, right? But once you start to make tiny nanoparticles out of the very same material, then it doesn't look like silver or gold anymore. And depending on the size of those particles, the light coming back from those particles are having different colors. I have here put a small explanation just for those of you who would think about what a nanometer is. You take 1 meter, you divide it by 1,000, You do it again, and you do it once more. Then you get to 1 nanometer. So those are roughly like 50 to 100 nanometers in size, meaning that they are, of course, far too small to be seen by the human eye. And yet, if we shine light on them, there's kind of this very distinct color coming back to us. This is another example. This time the particles are in a solution. And depending on their size and their shape, they manifest in quite different colors. So the hypothesis is that this beautiful glassware is kind of containing exactly such metallic nanostructures, particles inside, that makes the glass, in this case, appear greenish when we look at it from outside. And if we illuminate from inside, it appears red. So that's, of course, quite a postulate that the Egyptians and the Romans should be able to make such nanostructures and put them inside glass, right? But nevertheless, it turns out that this is very close to the explanation, in fact. So basically, you could probably say that nature has smiled to the people back in the old days. They have been working on making glass in basically the same way we make glass today. We mix sand and other substances, we heat it up, and then we kind of flatten it to get a piece of glass. But somewhere in this process, tiny pieces of metal has made its way into this process, maybe from the tools that they used for stirring, etc. And some guy out in the desert has had the right curiosity to actually pursue this further and explore exactly what kind of metal to add, how to grind it, how to get the right particles, etc. They have been collecting all the data to figure out how to routinely make red glass, greenish glass, blue glass, etc. Only equipped with sand and a few other things, the ability to heat up the material, etc. Isn't that amazing, actually? So what we are doing today is that we are trying to really replicate this in a much more controlled way. We are trying to make now the nanoparticles in a very controlled fashion in an environment where we keep track, make sure that there are no other particles really disturbing the thing. So to put it in perspective, the air inside such a clean room that is used for nanofabrication and making such tiny nanoparticles is kind of recirculated and filtered to the extent that there are only like 10,000 particles per cubic meter. So is there anybody who's kind of suffering from the spring and being allergic? I tell you, this is really heaven on earth being inside this clean room. If your nose is kind of dropping outside, if you enter, you're good. Okay, so we use these kind of facilities to really try to do what the people did in the old days. We don't make glass, but we try to make surfaces that we cover with such man-made artificial nanoparticles. So you should imagine now that you have a surface where you have deliberately put small metallic nanoparticles with some nanofabrication technique. And if we can control the size of each particle, we can basically control its color. So that means that this is becoming like now a Lego brick, if you like, where each of these dots can have a color on its own, depending on which kind of shape and size you made from the beginning. And that you can use, of course, for storing information in the shape of color images on a surface with tremendously high information density. And this has been used for instance, writing this picture of a woman from Sweden called Lena, who is now quite famous since everybody is using this picture apparently when printing things. But the key here is that those pictures are only like 100 microns by 100 microns, and yet we can, with very high resolution, print information. And if you think about storing information for the future, then think again about the glass windows and how long they have been sitting there without changing basically the information that the Egyptians and the Romans put into their glasses, right? there is a good indication that this information won't fade away over time, and people now considering really this kind of thing as a technology for storing huge amount of information in surfaces. Let me also give you another perspective on what you can actually do with this printing technique. Here I've put a table of different display technologies, and you don't have to look at the details, but basically it's telling you how many pixels you have per area in your device that you all carry in your pocket. And the most recent one and the best one, you can obviously tell that this is some promotion material by Apple, right? You can see that this Retina display can have a pixel size of around 100 microns by 100 microns. So that's already small. It looks fantastic when you look at this. The resolution is so kind of fine that you don't see really that it's kind of made out of pixels. And yet with our kind of technique, we can print this woman, Mona Lisa, right? On an area where this still fits into one single pixel on your iPhone. That gives you an impression how much information we can actually store on those kind of surfaces with this technique. Of course, you cannot see her with a human eye. You need tools for that. Let me give you another perspective. So we can make the nanostructures in the nanofabrication technology facility that we have, but we can also later on store further information in them. It turns out that even though this is not really changed by regular sunlight, if we shine special kind of light on this, where you use a laser like I have here, but emitting very short, ultra-energetic pulses of light, then you can use it to change basically each of those dots one after the other at a time. So you're feeding energy into this nanostructure, it's heating up, and then it's reshaping to form something that is more of a droplet. And if it changes shape, it changes color. So this is a principle for actually writing colors. And this movie running here in the background is showing how we are scanning such a laser and really adjusting the energy in each step, and thereby deciding which color each of the small dots should have. And that's being used to write now this logo from I should put myself here, write this logo from the International Year of Light. And basically, once you remove a small filter here, you see that, you have the image here written. So it's working very much like any other laser printer, except that it's not printing on white paper. It's printing on this very expensive metallic nanostructure surface. And it's printing with this tremendous spatial resolution. And just to put it in a perspective, a regular laser printer prints with like 600 dots per inch. And that's really sufficient. If you look at it with the human eye, you see a continuous kind of printing of your letters. But this printer here can print with a resolution that is exceeding this by several orders of magnitude. Again, it's a technology that is becoming available for storing information in such surfaces. And the ability to really rewrite this and add more information, etc., is paving the way for a lot of new applications in this area. Let me give you a more simple example here of how you can use such ideas to color materials that are from the beginning colorless. This is a piece of plastic. It's black from its beginning. It could be a Lego brick for that sake. And all the colors that you see here are actually not added by means of dye molecules. So no additional chemistry going into this product, but rather we have just made a lot of small trenches in the surface that causes light to scatter quite differently than a planar surface would. So it's entirely made from one piece of material, no additional molecules, and all the colors are only due to these kind of surface texture that you have in the surface. If I want to recirculate or recycle this material, it's only one piece of material. So I don't have to sort the different components before I can reuse it. If I grind it, it would just become black plastic again. And this is another example where you have taken a stainless steel surface, and again, all the colors you see here are just due to these kind of nanostructures. So you can imagine, of course, how there are a lot of companies that are kind of interested in these technologies now. Let me show you a more spectacular use of nanostructuring of surfaces. I should say it's a high-end product, so probably you have to pay quite a lot for such a piece of chocolate. But nevertheless, if you go to Switzerland, where they apparently have these kind of wishes, right? They actually made this kind of chocolate. So it's made in an injection mold. So like any regular piece of chocolate, you inject the chocolate into this mold, you let it cool down, and you take out the chocolate, right? So this chocolate mold has this additional feature that there are nanostructures, like I had in my previous slide, put into the mold, into the surface. So once you put chocolate into this and take it out, it will have a replication of this kind of nanostructure. And that's actually enough to cause all these beautiful colors here. No additional molecules, no chemistry here. You can safely eat this, even though it looks like something you shouldn't feed your kids with, right? It has this nice additional kind of feature. So imagine this quite likely situation. You're visiting family, right? And there's this nephew with not too clean fingers that is notoriously known for checking out all the chocolates before picking one, right? So those nanostructures will melt immediately when he's touching the piece. And so if it has no colors, it's not entirely unsuspicious, of course, and you know you should pick another one. I'm pretty sure there's a market for this kind of chocolate. Let me explain a little what causes all these colors. And you also saw the question, what the fuck is a plasmon? And so let me try to explain briefly. So you should imagine a piece of metal now. It could be a copper wire, a piece of silver or gold. This material has some electrons inside that are free to move. That's why it's a good electrical conductor. You can pull a current. You can make each electron move and carry a charge from one side to the other. But the electrons, they can also move collectively. They can all kind of move back and forth in this material. And if they do so, we call this kind of oscillation a plasmon. I'm sorry if you were expecting something more sexy, but that's really what it is. It's this collective oscillation or charge density wave of the electrons inside the piece of metal. And it's kind of resembling what is going on right now as I'm speaking to you guys out there. I'm also sending out a density wave that is existing in this compressible gas of atoms, molecules we have in here. And it's of course propagating as a wave. You can detect my voice in this way. And in the same way, the plasmon can propagate inside a piece of material as a wave. So it's not really that different. So think about a sound wave inside the metal, but the sound is carried by the electrons. Now that doesn't explain, of course, that the different sized particles have different colors. To really appreciate this, I have taken an example that probably many of you can relate to. It's a spring with a small mass at the end. And this will, of course, if I extend it away from its equilibrium position, it will start oscillate. And of course, depending on the mass, it can oscillate fast or slow. And your intuition should tell you that the smaller the mass, the faster it can oscillate. But if you put a heavy mass, it will oscillate slower. And if anybody is kind of uncertain about this, you should really, after the drinks, go home and try this, right? Find a good spring and put a mass, and then you check it. And with the metal nanoparticles, a little the same. You have the cloud of electrons that is oscillating around its equilibrium position. And depending on the size of those particles, you will have different resonance frequencies. And so here, nature kind of smiles at us if we make particles that are like 50, 100 nanometers, they happen to resonate in the visible part of the spectrum. And that's exactly what is happening inside those pieces of glass. You have 50 to 100 nanometer nanoparticles, and they resonate at a frequency where they can interact strongly with the light that comes in. So if the light has a frequency that fits nicely with this oscillation, it can be absorbed or it can be scattered depending on how you look at it. And it's really our ability to control those sizes that allow us to make different colors that rely on this principle. And I think it's absolutely spectacular that the Egyptians and the Romans could actually do the same. So let me remind you that a clean room like this is probably easily at the price of over the years, 1 billion Danish kroner, right? But the poor guy in the desert, he only needed a bucket and some wood he could light up, right? And then something to stir with, and then he could get glass out of that. I think it's really fantastic that they could make this process work and make it so perfect that we can enjoy it when we go into cathedrals and look at windows, or we visit these museums and look at stuff found from those days. Now, the reason that we can see all those nanostructures is basically due to this handsome guy here, Robert Hooke. And if there are any physicists here, they will know Hooke because he is also the guy who came up with what is known as Hooke's law. So that was at the time where you could make many discoveries. But basically, what Hooke did was absolutely fantastic. He figured out that if you make this optical instrument that we today know as a microscope, you can see tiny objects. And that's, of course, key to the developments in optics, but it's also something that basically couldn't imagine biology where we are today without optical microscopes, right? We desperately need those kind of instruments to see small objects. The question is, of course, how small objects you can see with an optical microscope. And basically, to appreciate that, you have to acknowledge that light is not just particles, light particles, but it can also be thought of as waves traveling in space, oscillating in space and time. So in the microscope, we have these kind of waves advancing. We let them interact with a tiny kind of object we like to study, and we see how light is coming back. And it's clear that if we shine this kind of light wave onto a very tiny object, it can be very difficult to really observe its kind of shape, etc., if it's much smaller than the wavelength of this wave. And that was something that was realized by this guy. Look at this beautiful, by Ernst Karl Abbe from Jena, who was one of the leading scientists in optics at that time, and was basically the guy driving the Zeiss company that many of you will probably have heard of. He figured out that there's a limit to that, which is called the diffraction limit. And the implication is that in an optical microscope, you can easily see if you put like insects. You can see the cross-section of a hair, you can see cells, bacteria, etc. But if you want to study vira, proteins, small molecules, or the nanostructures that I'm interested in, then you're in trouble. And basically, you cannot, with visible light, see things that are smaller than, say, 0.2 micrometer or 200 nanometers. And that's, of course, critical to the work I like to perform. If I put my nanostructures under the microscope, I see nothing. So I need another kind of microscope in my work that can push this diffraction limit to smaller length scales. I like to see the atoms, I like to see the nanostructures, etc. And there's actually hope that you can do that if you want to accept that you can work with other waves. So I want to have a microscope not operating with light, but some other waves. In this case, it's waves of electrons. And that's, of course, a kind of new paradigm, since we would often like to think about an electron as a small particle, right? And so the genius postulate by de Broglie, who was awarded the Nobel Prize in Physics, was to say that there's a particle-wave duality. So the guy sitting next to you could also not be a particle but a wave, and vice versa. And that's kind of a weird thing. And the most efficient way of actually convincing yourself, if you're in doubt, is to do the experiment. So quantum physics is often kind of difficult to appreciate, and if you find it difficult to appreciate, then go and do the experiment and see, well, it can actually replicate the observations we make. So de Broglie postulated that any particle that has a momentum can also have a wavelength and vice versa. And this is basically showing one experiment that you can do if you like to test if the electron can behave indeed as a wave. You send your electrons through a slit, and if it would have been light, you would get a diffraction pattern like here. So let's do it with electrons. And once you have sent in this case, it's 28 electrons. It doesn't look too promising, right? On your screen, you see a couple 28 dots here, right? Which makes us think more of this as like a particle that has been going through the slit. But then you are kind of patient for a while, and you send through more electrons. Once you reach 1,000 electrons, you start to see a pattern that reminds you of this kind of diffraction pattern. And if you send through even more, you build up statistics, and indeed, you end up in a situation where you conclude that in many ways, those electrons are behaving not only as particles, but also as waves. And once you accept this, you can, of course, make a microscope that is kind of using such waves. And if you can give them sufficiently short wavelength, you can deal with this diffraction limit. So the idea is to speed up the electrons, and let me show you how much we have to speed them up. Here I have basically calculated, according to de Broglie's postulate, what kind of wavelength an electron would have if I kick it by an acceleration voltage that is kind of increasing. So here I run it through a voltage which is 1 volt. That seems not like much. But already there you see the wavelength is pretty small. It's like 1 nanometer. If I go to like 100 kiloelectron volts, I have to measure this wavelength not in nanometers but picometers, right? I'm already far beyond the size of an atom here, which we measure in angstrom. So if I could make a microscope based on electrons, I could resolve even atoms in my microscope. And that's what I'm going to pursue. Let me just make a comment that we are actually accelerating those electrons to speeds where we're getting close to the speed of light. Meaning that work that Albert Einstein did is becoming relevant for this. We start to actually have relativistic effects in the systems. We have all these kind of different disciplines represented in this problem. We have quantum physics that will show up in a while. We have relativity, and we have Newton's law also, and Maxwell's equation. So it's really a wonderful playground for a theoretical physicist. Let me mention that many of you will probably attribute relativity to Einstein, but that was not what he was awarded the Nobel Prize for. So here's the electron microscope, and honor should go to Ernst Ruska, who got the Nobel Prize for actually making this instrument and making it work. It's very much like an optical microscope, but working now with a beam of electrons passing through. And this is like a 15 million kroner Danish beast standing out at DTU campus, where you can actually do now these kind of experiments. And let me right away show the kind of physics. So since there will be music afterwards, I thought it was kind of great to bring a problem with string instruments. And I will show you that the physics we can explore in those systems are very much resembling the physics you meet if you are trying to play the guitar or if you are trying to make this. So how many of you would have a rope of 2.5 meters at home? There's at least one up there. Great. I really recommend that you all go home after the bar and try to do this. Try to tie up the rope at one end, find a good tree in the garden, and then you go like this, and you find the right frequency, right? And then you will see these standing waves. How many has tried this already? Okay, there's a few who should go home and do it, right? I will try to do the same now with the plasmons in my system. So it's very much the same physics. So here it is. This is not it's my kind of guitar string, if you like. It's a long, thin wire of silver. It's like a few hundred nanometers long. I'm not going to excite sound waves in this, so this is not the string I will do like that. I will instead make the electrons oscillate back and forth, so the plasmon that will form these kind of standing waves here. And the way I will do the experiment is as follows. I will put it in my electron microscope that I have already used to image this wire, and then I will come in with a beam of electrons with a high energy, which will lose a small fraction of its energy to exciting these plasmons that are kind of flushing back and forth in the wire. And at the same time, I will scan my beam along the wire like this, so I can really map out these kind of oscillations. So if you're all ready, I will show you how this actually looks if you go to the very nanoscale. And you will be very disappointed because it looks exactly like the guitar string. Same kind of physics, now manifested in a very short silver nanowire. We can count together. Here I have an example where I have 2 times half the wavelength fitting with the length of this wire. Here I have 3 kind of maxima. There's an example with 4, etc. So it's really the same kind of things we are doing. And from a research point of view, we were kind of extremely excited to be able to resolve this and show it. On the other hand, it's of course just confirming what we knew already. There are not that many surprises there. And so what we decided was to push for even smaller systems, to start to see something that is not resembling what we can do with a guitar string or 2.5 meter of rope in the back garden. So another kind of thing you could try to do is this kind of phenomena that you can also kind of experience if you go to a cathedral. So the cathedral is apparently a wonderful playground for many of those things. There's a phenomena called whispering gallery modes, and it goes like follows. If you put yourself in the cathedral near the wall and you start kind of shouting, of course you shouldn't do that in a cathedral, right? But nevertheless, if you do it, you send out sound waves, and if you adjust your voice, the frequency of your voice, so that the wavelength would fit with the perimeter of this cathedral, you can end up having these kind of periodic orbits, right? Standing waves, not along a wire, but now going around this kind of circular cavity. And that also implies that if you are standing here and you put your mother over here, right, she would hear nothing. But if you move her a little further to the right, she would be able to hear something. I think this is fantastic manifestation of these kind of standing wave phenomena. And if you haven't tried, you should absolutely do it when you're in London next time. Okay, the same physics must have inspired Niels Bohr when he wanted to actually address how electrons are now orbiting around the positively charged nucleus of the atom. He thought about this electron now having wave properties, just like de Broglie described. And basically, there are special solutions to this problem when the wave is kind of fitting with itself when you're going one turn around, right? And that forms these kind of discrete energy levels that can be observed, for instance, if you look at hydrogen, the light coming out of that. And so we were curious in our research if we could make a new version of this. And so basically what we are imagining now is kind of not wires of silver, but tiny particles of silver. So you see one example of such a particle up here. And basically, we now have the plasmons not flushing back and forth, but traveling around the perimeter of this sphere, right? Very much like the electrons are orbiting around the positively charged nucleus. But in this case, it's not like looking at one electron, but all the electrons doing the same collective motion. And basically, our experiments show exactly such kind of phenomena. And when we are pushing to smaller and smaller particles, we also start to see some dynamics that we cannot really explain with a classical theory. And we see this as a completely new avenue where we can explore also quantum effects in these systems. And we can indeed expect that things should happen. So up here I put a scale bar of 5 nanometers, meaning this particle is only 5 nanometers, right? But if you look carefully, some of you would probably say this is a quite poor picture. I mean, But what you see here, all the small dots are actually the individual atoms. So I couldn't have made a better picture. And actually it tells you that you should start treating this system with the same kind of methods that we are treating, that Bohr was treating his individual atoms, right? We are really tapping into a new regime where you would expect to see that electrons are not only moving according to Newton's second law, but they are obeying some new kind of physics. And that's what we are very curious now to explore. Let me just give you another example. It's a collection of two particles, and basically here you again see the indication of the individual atoms telling you that something new should indeed happen. And what I'm really kind of now pursuing in my research is an understanding of what happens when you cross this kind of border from, say, the classical world that we all get up to every morning, right? Alarm clock rings, you jump out. It's all governed by Newton's second law, right? And then on the other side, this fascinating world of Niels Bohr and his atoms and the quantum mechanical description of that. And in particular, I like to really understand what happens when we cross this border. And so you see there is some border control here. And I want to know what happens there. Good. Let me give you one final example how extreme this can now be done. We can make very small particles, but we can also make a flat version of that. We can make sheets of material that is only one atom thin. So it cannot be thinner, simply. And at the same time, we make kind of small disks out of that, and we explore how electrons are flushing around in those systems, and we start to see that indeed such atomic systems need a completely new treatment, and still they can be used for basically controlling the color that we see once light is interacting with those systems. And this is maybe just an appetizer, and since we will soon have music, why don't we call this a nanodrum? It's a sheet of one atom thin material that can contain these electrons, but can also kind of vibrate just like the loudspeaker, the membrane in a loudspeaker. And as we speak, people are actually making these membranes. And it gives this fantastic opportunity for studying systems where you have the light interacting with other degrees of freedom in the system, like vibrations. Let me just finally make a few comments on people who really contributed to the society we have today, but which are probably not kind of recognized in a broader sense. John Bardeen was kind of a special guy in the sense that he had to receive a call from Stockholm twice. Isn't that amazing? He basically invented the transistor, which you all carry in your pocket in the form of a cell phone. And later on, he again revolutionized not only the field of physics, but science in general by discovering or coming up with a theory of superconductivity. And basically, this is the reason that we have quantum technology today. And my claim as we are reaching out for the drinks is that you actually have your pockets loaded with quantum technology and more will come. And let me just mention how it comes. We communicate with each other through light, which involves a laser, which is a quantum system. We need atomic clocks for the GPS systems that are kind of keeping track of where we have our cell phones. And of course, without the quantum theory of materials and the understanding leading to the transistor, we wouldn't even have computers and cell phones. And right now, people are very excited about the next wave in this, where we start to see even more quantum technology making it into our lives. And in my research, we have this kind of dream that we can make systems so small that you see both the light exhibiting quantum mechanical properties and the materials. And in this direction, we see a lot of the new quantum technology coming. So with this, I only want to kind of thank you for your attention, but also, of course, mention that all the research I'm doing is only possible actually because there are people who are so generous to support me, And in particular, I'd like to thank the Willem Foundation, which is a private foundation that is now really fueling a lot of money back into society and research. And it all happens because the inventor of the Velux window decided that this should benefit the entire society. And with this, I'd just like to, again, thank you for coming. I don't want to reach into the session with drinks, and I'm happy to take your questions. Thank you.